Hello, in this lecture we'll answer two questions. In the first question, we'll find out the area of this semicircle that is inside the quarter circle AOB. And in the second question, we'll find out the area of this green shape that is inside rectangle ABCD. So we'll start with the first question. So in the drawing we have a quarter circle, AOB is a quarter circle. We know that side AO equals to 5 units in its length. Inside this quarter circle AOB we have this semicircle, and our mission is to find out the area of this semicircle. So first of all, when we define the center of this semicircle, this point is point C. Likewise, we will define the touching point of the semicircle with this quarter circle. This point is point F. We will define the touching point of this semicircle with this quarter circle. This point is point G. We will define the point of tendency of tangent AO with this semicircle. This point is point E. And finally, we define the point of tendency of tangent BO with this semicircle. This point is point L. We know that AO equals to 5 units in its length. That is to say, the radius of this quarter circle is equal to 5 units. We will define the radius of this semicircle as x. So CF equals to CG, they are both the area of this semicircle. That equals to x according to our definition. Therefore CF equals to x. And the radius CG of this semicircle also equals to x according to our definition. In the next step, we will join points C and M together by a straight line. So CL is the radius of the semicircle because it starts from point C, that is the center of the semicircle, and ends at point L, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore Cn is the radius of this semicircle, is equals to x according to our definition. Likewise, we join point C and F together by a straight line. So actually, CF, we join point C and E together by a straight line. So CE is also the radius of this semicircle, that equals to x according to our definition. So here we have the radius CE the radius CE is drawn to point E, that is the point of tendency of tangent AO with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius EC. If AO is perpendicular to EC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius CL of this semicircle, and the radius CL that equals to x is drawn to point L, that is the point of tendency of tangent BO with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent BO will be perpendicular to the radius LC. If BO is perpendicular to LC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So actually, by doing these constructions, we can do the quadrilateral CEOL. Inside this quadrilateral CEOL, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth piece in angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth piece in angle must be equal to 90 degrees in its size. So inside quadrilateral CEOL we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle if not a square. So we will relate to quadrilateral CEOL as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle CEOL, side CE must be equal to the opposite side LO. But CE is x, therefore LO must be also equal to x. Likewise, according to the same rule, in the same rectangle CEOL, side CL must be equal to the opposite side EO. But CL is x, therefore EO must be also equal to x. So if we found out that rectangle, that quadrilateral CEOL is not a rectangle but a square, well, because of the fact that all of its sides are equal to each other. So in the next step, we'll join points O and C together by a straight line. By joining points O and C, we can do the right triangle, triangle CLO. Triangle CLO is also an associated triangle because of the fact that CL equals to LO. So I'll copy the right and associated triangle, triangle CLO in a new page, and we'll implement the Pythagoras theorem of this right and associated triangle, triangle CLO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the proportion for Pythagoras theorem. So actually, this is the right and associated triangle, triangle CLO, that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle CLO, CO square equals to CL square plus LO square. So I write it down. So CO squared, that is the square of the hypotenuse, must be equal to CL squared plus LO squared. CO is the missing side, so leave it as it is. So it is CO squared equals to CL squared. CL is x, therefore CL squared is x squared plus LO squared. LO is also x, therefore LO squared is x squared. So in total, CO squared equals to x squared plus x squared. X squared plus x squared is 2x squared. So if we found out that CO squared equals to 2x squared. So here we take a root out of this equation, and finally we get that the missing hypotenuse CO, the length of the missing hypotenuse CO is equals to the square root of 2 times x units in its length. So actually, this is CO, and the length of this line 7 CO is square root of 2 times x units. Actually, point O is the center of the quarter circle, and from the center of the quarter circle, that is to say from point O, we have line segment OC that bisects chord GF. Again, from the center of the quarter circle, that is to say from point O, we have here line segment OF, line segment OC that bisects chord GF. Why line segment OC bisects chord GF? Because of the fact that CG equals to CF. So line segment OC bisects chord GF into two halves. Each half equals to x. CG equals to CF equals to x. And whenever we have a line segment that is drawn from the center of a circle and it bisects a chord, we can implement rule 7. So I'll repeat quickly on rule 7. According to rule 7, if a line segment that is drawn from the center of the circle bisects the chord, then the line segment is perpendicular to that chord. So in the drawing we have a circle. This is point O, that is the center of the circle. So from the center of the circle, that is to say from this point O, we have line segment OM that bisects chord AB. One line segment OM bisects chord AB because of the fact that MO equals to MB. And because of the fact that line segment OM bisects chord AB, line segment OM will be also perpendicular to AB. So if OM is perpendicular to AB, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 7. So whenever you have a line segment that is drawn from the center of the circle and it bisects a chord, it will be also perpendicular to that chord. In this case, line segment OM bisects chord AB, and therefore line segment OM will be also perpendicular to chord AB. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 7. So we can actually implement rule 7 in our drawing. Why? Because in our drawing, we have line segment OC that bisects chord FG. And whenever you have a line segment that bisects a chord, and it is drawn from the center of the quarter circle, that is to say from point O, then that line segment will be also perpendicular to chord FG. So according to rule 7, line segment OC will be also perpendicular to FG. If OC is perpendicular to FG, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 7. In the next step, we will join points O and F together by a straight line. What is the definition of line segment OF? Line segment OF starts from point O, that is the center of this quarter circle, and ends at point F, that is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, OF is the radius of this quarter circle, and according to what is given as the question, the radius of this quarter circle equals to 5, because AO equals to 5. And therefore, OF is the radius of the quarter circle, that is equals to 5 units in its length. In the next step, I'll copy this green right triangle CFO in a new page, and we'll implement the Pythagoras theorem on this green right triangle CFO. Here by PT is the version for Pythagoras theorem. So actually, this is the right green triangle, triangle CFO, that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle CFO, FO squared, that is the square of the hypotenuse, must be equal to FC squared plus CO squared. Again, FO squared equals to FC squared plus CO squared. So write it down. According to the Pythagoras theorem, in this right triangle, triangle CFO, CF squared, that is the square of the hypotenuse, must be equal to actually FO squared. That is, the hypotenuse is FO, therefore FO squared must be equal to FC squared plus CO squared. The hypotenuse FO is 5, therefore FO squared is 5 squared, that is 25. So 25 equals to FC squared. FC is x, therefore FC squared is x squared plus CO squared. CO is 2 square root of 2 times x, therefore CO squared is square root of 2x squared. This actually equals to 2x squared. For conclusion, we found out that 25 equals to x squared plus 2x squared. X squared plus 2x squared is 3x squared. So in total we found out that 25 equals to 3x squared. Here we divide this equation by 3, and finally we get that x squared equals to 25 over 3. Again, x squared equals to 25 over 3. Our mission is to find out the area of this semicircle. What is the area of the semicircle? We know that the radius of this semicircle is x, and therefore the area of the semicircle will be equal to pi x squared over 2. So I write it down. The area of the semicircle will be equal to pi x squared, that is the area of the circle, divided by 2. So the area of the semicircle equals to pi over 2 times x squared. And we just right now found out that x squared equals to 25 over 3. Therefore, we can substitute x squared in this equation by 25 over 3. We'll do it now, and we get that the area of the semicircle will be equal to pi over 2, and x squared is 25 over 3. So in total, the area of the semicircle will be equal to 25 pi over 2 times 3. 2 times 3 is 6. So in total, we will find out that the area of this semicircle equals to either 25 pi over 6 square units, or in terms of numbers, it is equals to 13.09 square units. And that's the question. Okay, again, if we found out that the area of this semicircle is equal to either 25 pi over 6 square units, or in terms of numbers, it is equal to 13.09 square units. So we finished with the first question. In the next step, I present to you the second question, and we'll answer on the second question. Our mission is in the second question is to find out the area of this green shape. So in the drawing, we have rectangle ABCD. We know that side AB of rectangle ABCD equals to 5 units in its length. And our mission is to find out the area of this green shape. So first of all, in addition, actually, inside rectangle ABCD, we have this semicircle and this quarter circle. Again, our mission is to find out the area of this green shape. So we will define the radius of this quarter circle, BC, as x. Again, according to our definition, the radius of this quarter circle, BPC, equals to x. But we know that ABCD is a rectangle, and the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side BC must be equal to the opposite side AD. But BC equals to x, therefore AD must be also equal to x. AD is one side of rectangle ABCD, but AD is also the diameter of the semicircle. So the diameter AD equals to x units in its length. If the diameter AD equals to x, it means that the radius of this semicircle must be equal to half of it. That is to say, the radius is x over 2. So the radius of this semicircle is x over 2. We define the center of this semicircle as O. So just like I found out that the radius OA of this semicircle equals to x over 2 units in its length. Likewise, the radius OD of this semicircle also equals to x over 2 units in its length. According to the rule that the opposite sides of a rectangle are equal to each other, we get that in rectangle ABCD, side AB must be equal to the opposite side DC. But AB is 5, therefore DC must be also equal to 5 units in its length. So I write it down. Side DC equals to 5 units in its length. So in the drawing, we have an external length between this semicircle and this quarter circle. That is to say, they touch each other externally at this point. So we define their touching point as point S. And whenever you have an external length between two circles or two semicircles, you can implement Rule 10. So I repeat quickly on Rule 10. According to Rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching point. So in the drawing we have two circles. Those two circles have an external notch between them at point P. That is to say, they touch each other externally at this point P. The center of this circle is here at point O. The center of this circle is here at point M. And the straight line that connects their centers together is of course the straight line OM. And according to this rule 10, the straight line OM must pass through point P, that is their touching point. Again, the straight line OM must pass through point P, that is their touching point. Or OPM is one straight line. Again, OPM is one straight line according to this rule 10. So we can actually implement rule 10 in our drawing. Why? Because in our drawing we have an external notch between this semicircle and this quarter circle. That is to say, they touch each other externally in this point S. Therefore, we can implement a rule 10. The center of this semicircle is here at point O. The center of this quarter circle is here at point C. And the straight line that connects the centers together is of course the straight line OC. And the straight line OC, according to rule 10, must pass through point S, that is their touching point. Again, the straight line OC must pass for their touching point, that is point S. Or OSC is one straight line. Again, OSC is one straight line. So we join points O and C together by straight line, and according to rule 10, the straight line OC must pass through point S, that is their touching point. So you can see in the drawing that the straight line OC, that connects their centers together, passes from point S, that is their touching point. So because of the fact that OSC is one straight line, according to rule 10, it means that OC will be equal to OS plus SC. Again, OC will be equal to OS plus SC. So I write it down. OC equals to OS plus SC. So OC equals to OS. What is the definition of line segment OS? Line segment OS starts from point O, that is the center of this semicircle, and that's at point S, that is the point on the semicircle itself. So this is exactly the definition of a radius. Therefore, OS is the radius of this semicircle, is equals to x over 2. So here, OC equals to OS. OS is x over 2 plus SC. What is the definition of line segment SC? Line segment SC starts from point C, that is the center of this quarter circle, and ends at point S, that is a point on the quarter circle itself. So this is exactly the definition of a radius. Therefore, CS is the radius of this quarter circle, is equals to x according to our definition. So CS equals to x. So in total we can find out that OC equals to x over 2 plus x. X over 2 plus x is 1.5x, so 3 over 2x. So we can find out that OC equals to 3 over 2x units in its length. So the hypotenuse OC of the right triangle. First of all, we know that all the angles in any rectangle are right angles, and therefore this angle is a right angle. So if we found out that the hypotenuse OC of the right triangle ODC is equals to 3 over 2x units in its length. In the next step, I'll copy the right triangle ODC in a new page, and we'll implement the Pythagoras theorem on this right triangle ODC. Here by PT is the version for Pythagoras theorem. side OD equals to x over 2 units in its length, side DC equals to 5 units in its length, and just like now found out that the hypotenuse OC equals to 3 over 2x units in its length. Carefully, this is the right triangle ODC that is coming from the original domain. According to the Pythagoras theorem, in this right triangle ODC, OC squared equals to OD squared plus DC squared. Again, OC squared equals to OD squared plus DC squared. So I write it down. OC squared, that is the square of the hypotenuse, equals to OD squared plus DC squared. The hypotenuse OC equals to 3 over 2 times x units in its length, and therefore OC squared equals to 3 over 2x squared. 3 over 2x squared equals to 9 over 4x squared, and it is equals to OD squared. OD is x over 2, therefore OD squared is x over 2 squared, that is x squared over 4 plus DC squared. DC is 5, therefore DC squared is 5 squared, that is 25. So in total we found out that 9 quarters times x squared equals to 1 quarter x squared plus 25. Here we subtract x squared minus 4, x squared over 4 from this equation, and we get that 9 quarters x squared minus 1 quarter x squared equals to 8 quarters x squared, and it is equals to 25. So 8 quarters x squared equals to 25. 8 over 4 is 2, so this expression in total will be equal to 2x squared, and 2x squared equals to 25. Here we'll divide this equation by 2, and finally we get that x squared equals to 25 over 2. X squared equals to 25 over 2. So here we take a root out of this equation, and finally we get that x equals to the square root of 25, that is 5, over square root of 2. So in conclusion, we should find out that x equals to 5 over square root of 2 units in its length, and x squared equals to 25 over 2. Our mission is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of the green shape in total will be equal to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. So in conclusion, we have found out that the area of the green shape in total equals to the area of rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. So the area of the green shape equals to the area of rectangle ABCD. What is the area of rectangle ABCD? Actually, the area of any rectangle equals to the length of the rectangle times the width. The length of this rectangle ABCD is 5, and the width is x. So in total, the area of rectangle ABCD equals to 5x. So again, the area of rectangle ABCD equals to 5x minus the area of the semicircle. What is the area of this semicircle? We know that the radius of this semicircle is x over 2. And therefore, the area will be equal to pi times x over 2 squared divided by 2. So the area of the semicircle equals to pi times the radius squared, that is x over 2 squared divided by 2, minus the area of this quarter circle. What is the area of this quarter circle? We know that the radius of the quarter circle is x. Therefore, the area of the circle is pi x squared. And because of the fact that the area of the circle is pi x squared, the area of the quarter circle will be equal to pi x squared over 4. In conclusion, we found out that the area of the quarter circle equals to pi x squared over 4. So okay, the value of this expression is equal to the area of the green shape. So this expression equals to 5x, and here we have pi x over 2 squared. X over 2 squared equals to x squared over 4. So in total, this expression will be equal to pi x squared over 4 divided by 2 minus pi x squared over 4. So the area of the green shape in total equals to 5x. Here we have minus pi x squared over 2 times 4 is 8. So in total this expression equals to minus pi x squared over 8. Here we will multiply both the numerator and the denominator of this expression by 2 in order to have a common factor with this expression. So after we multiply both the numerator and the denominator of this expression by 2, we get that this expression will be equal to minus 2 pi x squared divided by 8. So in total, the area of the green shape equals to 5x minus pi x squared over 8 minus 2 pi x squared over 8. So it is equals to 5x, and minus pi x squared over 8 minus 2 pi x squared over 8 equals to minus 3 pi x squared over 8. So in total, we found out that the area of the green shape equals to 5x minus 3 pi x squared over 8. But we have already found out that x equals to 5 over square root of 2 units in its length, and x squared equals to 25 over 2. Therefore, we substitute x in this equation by 5 over square root of 2, and x squared in this expression by 25 over 2. We'll do it now, and we get that the area of the green shape in total equals to 5x, and x is 5 over square root of 2 minus 3 pi over 8 times x squared, and x squared is 25 over 2. So in total, we should find out that the area of the green shape equals to 5 times 5 over square root of 2 minus 3 pi over 8 times 25 over 2. So 5 times 5 is 25, so in total this expression equals to 25 over square root of 2 minus 3 pi over 8 times 25 over 2. Minus 3 pi times 25 is minus 75 pi, and in the denominator we have 2 times 8, that is 16. So today we found out that the area of the green shape equals to 25 minus square root of 2. Again, it is equals to 25 over square root of 2 minus 75 pi over 16 square units. In terms of numbers, this expression equals to 2.95 square units. And that is the answer to the question. And again, we should find out that the area of this ring shape equals to either 25 over square root of 2 minus 35 pi over 16 square units. So in terms of numbers, the area of this ring shape equals to 2.95 square units. So we finished with the second question. In the next step, I will summarize the lecture. We start with the first question, of course. In the first question, our mission was to find out the area of this semicircle that is inside this quarter circle AOB. So in the domain we have quarter circle AOB. You know that AO equals to 5 units in its length. That is to say the radius of this quarter circle is 5. So inside this quarter circle we have this semicircle. And our mission is to find out the area of this semicircle. So first of all, we define the center of this semicircle, this point as point C. We define the touching point of this semicircle with this quarter circle, this point as point F. We define the other touching point of this quarter circle with this semicircle, this point as point G. We define the point of tendency of tangent BO with this semicircle, this point as point L, and finally we define the point of tendency of tangent AO with this semicircle, this point as point E. In the next step, we define the radius of this semicircle as X. Therefore, CF equals to CG. They are both the radii of this semicircle. This is equals to X according to our definition. So each of them is equals to X. Likewise, we join point C and L together by a straight line. CL is also the radius of this quarter circle. That is equal to X according to our definition. We join point C and E together by a straight line. CE is also the radius of this quarter circle. That is equal to X. So here we have the radius CE is drawn to point E, that is the point of tendency of tangent AO with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius EC. If AO is perpendicular to EC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius CL of this semicircle that is equals to X. The radius CL is drawn to point L, that is the point of tendency of tangent BO with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent BO will be perpendicular to the radius LC. If BO is perpendicular to LC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So by doing these constructions, we created a quadrilateral CEOL. Inside this quadrilateral CEOL, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 facing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 facing angle must be equal to 90 degrees in its size. So inside quadrilateral CEOL, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be a rectangle, if not a square. So we will write to quadrilateral CEOL as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle CEOL, side CE must be equal to the opposite side OL. But CE is X, therefore OL must be also equal to X. Likewise, according to the same rule, in the same rectangle CEOL, side CL must be equal to the opposite side EO. But CL is X, therefore EO must be also equal to X. So actually found out that quadrilateral CEOL is not a rectangle but a square, because of the fact that all of its sides are equal to each other, its side is equal to X. In the next step, we join points O and C together by straight line. By doing this construction, we created the right triangle CLO. The right triangle CLO is also an associated triangle because CL equals to LO equals to X. In the next step, I copied the right triangle CLO in a new page, and we implemented the Pythagoras theorem on this right and associated triangle CLO. So actually, this is the right and associated triangle CLO, that are going to the original drawing. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle CLO is CO, and therefore the square of the hypotenuse is CO square, and CO square must be equal to CL square plus LO square. Again, CO square equals to CL square plus LO square. CO is the missing side, so we leave it as it is. So CO square equals to CL square. CL is x, therefore CL square is x square plus LO square. LO is x, therefore LO square is x square. So in total, we found out that CO square equals to x square plus x square, that is 2x square. So CO square equals to 2x square. We took out of this equation, and finally found out that CO, the missing bottom CO, is equals to the square root of 2 times x units in its length. So this is the missing hypotenuse CO, that is equals to the square root of 2 times x units in its length. So in the drawing, we have, this is line segment OC that exists from point O, that is the center of the quarter circle, and line segment OC bisect chord FG. Why line segment OC bisect chord FG? Because of the fact that CG equals to CF. So line segment OC bisect chord GF into two halves. Each half equals to x. CG equals to x, and CF also equals to x. And whenever you have a line segment that exists from the center of the circle or semicircle or quarter circle and bisect the chord, you can implement rule 7. So I'll be clicking on rule 7. According to rule 7, if a line segment that is drawn from the center of the circle bisects the chord, then the line segment is perpendicular to that chord. So in the drawing, we have a circle. The center of the circle is here at point O. From the center of the circle, that is to say from this point O, we have a line segment OM that bisects chord AB. That is to say, MA equals to MB. And because of the fact that line segment OM bisects chord AB, line segment OM will be also perpendicular to AB. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 7. So whenever you have a line segment that bisects a chord, then the line segment will be also perpendicular to that chord. And it also must exist from the center of the circle, like here. So if we can implement rule 7 in our drawing. Why? Because in our drawing, from the center of the quarter circle, that is to say from point O, we have a line segment OC that bisects chord FG. That is to say, divided into two halves. Each half equals to x. CF equals to CG equals to x. And therefore, according to rule 7, line segment OC will be also perpendicular to chord FG. If OC is perpendicular to FG, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 7. In the next step, we join points O and F together by straight line. By joining points O and F, we can get here the right triangle CFO. What is the definition of line segment OF? Line segment OF starts from point O, that is the center of the quarter circle, and ends at point F, that is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, OF is the radius of this quarter circle. That is equals to 5 according to what is given as the question. So in the next step, I copied the right green triangle CFO in a new page and implemented the Pythagoras theorem on this right green triangle CFO. So actually, this is the right green triangle CFO that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle CFO, FO square equals to CO square plus CF square. Again, FO square, that is the square of the hypotenuse, must be equal to CO square plus CF square. Or FO square equals to FC square plus CO square. FO is 5, therefore FO square is 5 square, that is 25, and it is equals to FC square. FC is x, therefore FC square is x square plus CO square. CO is square root of 2 times x, therefore CO square is square root of 2 times x squared, that is actually 2x squared. So in total, we shall find out that 25 equals to x squared plus 2x squared. X squared plus 2x squared is 3x squared, so 25 equals to 3x squared. We divided this equation by 3, and finally found out that x squared equals to 25 over 3. Again, x squared equals to 25 over 3. So our mission is to find out the area of this semicircle. The area of the semicircle will be equal to pi x squared over 2 because the radius is x. So the area of this semicircle equals to pi x squared over 2. And again, the area of the semicircle equals to pi x squared over 2. So it is pi over 2 times x squared. And we just right now found out that x squared equals to 25 over 3. Therefore, we can substitute x squared in this equation by 25 over 3. We did it, and we should found out that the area of the semicircle in total equals to pi over 2, and x squared is 25 over 3. So in total, the area of the semicircle equals to 25 pi, 2 times 3 is 6. So it is 25 pi over 6 square units. In terms of numbers, the area of this semicircle equals to 13.09 square units. So we finished with the first question. Next step, I could present it to the second question, and we solve the second question. Our mission in the second question is to find out the area of this green shape. So in the drawing we have rectangle ABCD. We know that side AB of this rectangle ABCD equals to 5 units in its length. Inside this rectangle ABCD we have this semicircle and this quarter circle, and they touch each other externally at point S. That is to say they have externals between them at point S. Again, our mission is to find out the area of this green shape. So first of all, we define the radius of this quarter circle as x. So BC, that is the radius of the quarter circle, equals to x according to our definition. But in rectangle ABCD, we know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side BC must be equal to the opposite side AD. But BC is x, therefore AD must be also equal to x. AD is one side of rectangle ABCD, but AD is also the diameter of this semicircle. So we know that the diameter of this semicircle equals to x. If the diameter is x, it means that the radius must be equal to half of it. So the radius is x over 2. So the radius of this semicircle is x over 2. We define the center of this semicircle as O. Therefore, the radius OA equals to x over 2, and the radius OD of this semicircle also equals to x over 2 units in its length. We know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC, but AB is 5, therefore DC is also 5. We know that all the angles inside the rectangle are right angles, so this angle is a right angle. It is 1 out of 4 angles inside rectangle ABCD, therefore it is a right angle. So we have, so I already mentioned before, we have an external between this semicircle and this quarter circle. That is to say they touch each other externally at point S. And whenever you have external between two circles or semicircles, you can implement rule 10. So I'll click quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects the centers together passes through their touching points. So in the drawing we have those two circles, and they touch each other externally at this point, point P. So they have externals between them at point P. The center of this circle is there at point O. The center of this circle is there at point M. And the straight line that connects the centers together is of course the straight line OM. And according to this rule 10, the straight line OM must pass through their touching point, that is point P. Again, the straight line OM must pass through their touching point, that is point P. Or OPM is one straight line. Again, according to this rule 10, OPM is one straight line. So we can actually implement rule 10 in our drawing. Why? Because in our drawing, we have an external between this semicircle and this quarter circle, that is to say they touch each other externally at point S. Therefore, we can implement here rule 10. The center of this semicircle is there at point O. The center of this quarter circle is there at point C. The straight line that connects the centers together is of course the straight line OC. And the straight line OC, according to rule 10, must pass through point S, that is their touching point. Again, the straight line OC must pass through their touching point, that is point S. Or OSC is one straight line. Again, OSC is one straight line according to rule 10. If OSC is one straight line, it means that OC will be equal to OS plus SC. Again, OC equals to OS plus SC according to rule 10. So OC equals to OS. OS is the radius of this semicircle, that is x over 2. So OS is x over 2 plus SC. SC is the radius of this quarter circle, that is x according to our definition. So in total, OC equals to OS, that is x over 2, plus SC, that is x. So in total, OC equals to x over 2 plus x, that is 1.5x, or 3 over 2x. So if you found out that OC equals to 3 over 2x units in its length. In the next step, I copied the right triangle ODC in a new page and implemented the Pythagoras theorem on this right triangle ODC. So this is the right triangle ODC that I copied from the original drawing. The hypotenuse OC equals to 3 over 2x units in its length, OD equals to x over 2, and DC equals to 5. According to the Pythagoras theorem in this right triangle ODC, OC square equals to OD square plus DC square. Again, OC square equals to OD square plus DC square. OC is 3 over 2x, therefore OC squared is 3 over 2 times x squared, that is 9 over 4x squared, and it is equals to OD squared. OD is x over 2, therefore OD squared is x over 2 squared, that is x squared over 4, plus DC squared. DC is 5, therefore DC squared is 5 squared, that is 25. So in total, we actually found out that 9 quarters x squared equals to 1 quarter x squared plus 25. Here we subtracted x squared over 4 from this equation, and finally found out that 9 quarters x squared minus 1 quarter x squared equals to 8 quarters x squared, and it is equal to 25. 8 over 4 is 2, so in total this expression equals to 2x squared, that is equals to 25. Here we divided this equation by 2 and finally found out that x squared equals to 25 over 2. Here we took out of this equation and finally we get that x equals to the square root of 25, that is 5, over square root of 2. So in total we should found out that x squared equals to 25 over 2 and x equals to 5 over square root of 2 units in its length. Our mission is to find out the area of this green shape. So what is the area of the green shape? From the drawing it is very easy to see that the area of this green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of the quarter circle. So if you again, the area of the green shape in total equals to the area of rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. So the area of the green shape equals to the area of rectangle ABCD. What is the area of rectangle ABCD? We know that the area of any rectangle equals to the length of the rectangle times the width. The length AB is 5, the width BC is x, therefore in total the length times the width is 5x. So the area of rectangle ABCD is 5x, minus the area of this semicircle. The radius of this semicircle is x over 2, and therefore the area of this semicircle will be equal to pi times the radius squared over 2. So it is pi times x over 2 squared divided by 2. So in total the area of the semicircle equals to pi times the radius squared, that is x over 2 squared divided by 2. Minus the area of the quarter circle. What is the area of the quarter circle? We know that the radius of the quarter circle is x. And therefore the area of the quarter circle will be equal to pi x squared over 4. So the area of the quarter circle equals to pi x squared over 4. So in total the area of this green shape is equals to this expression, and this expression equals to 5x, and here we have pi x over 2 squared is x squared over 4. So in total this expression will be equal to pi x squared over 4 multiplied by 2. So it is pi x squared over 4 multiplied by 2 minus pi x squared over 4. So the area of the green shape in total equals to 5x. Here, this expression in total equals to pi x squared over 2 times 4 is 8. So it is pi x squared over 4. Here we multiplied both the numerator and the denominator of this expression by 2. After we multiplied both the numerator and the denominator by 2, this expression will be equal to minus 2 pi x squared over 8. So in total, the area of the green shape equals to 5x. And we have minus pi x squared over 8 minus 2 pi x squared over 8 is minus 3 pi x squared over 8. So in total the area of the green shape equals to 5x minus 3 pi x squared over 8. We already found out that x equals to 5 over square root of 2 and x squared equals to 25 over 2. Therefore we can substitute x in this equation by 5 over square root of 2, and x squared in this expression by 25 over 2. We did it and actually found out that they are, the Green shape equals in total to 5x, and x is 5 over square root of 2 minus 3 pi over 8 times x squared, and x squared is 25 over 2. So in total they have the Green shape equals to 5 times 5 over square root of 2 minus 3 pi over 8 times 25 over 2. 5 times 5 is 25, so in total this expression equals to 25 over square root of 2, and we have here minus 3 pi times 25 is minus 75 pi, and in the denominator we have 8 times 2, that is 16. So in total this expression equals to 75 pi over 16. So in total they have the Green shape equals to 25 over square root of 2 minus 75 pi over 16 square units. In terms of numbers, the value of this expression in total equals to 2.95 square units. So in conclusion, we should find out that the area of this Green shape equals to 2.95 square units. Okay, thank you very much.